morning. In this session, we evaluate the Haber process, the process for the large-scale manufacture of ammonia gas. Welcome. Ammonia gas is a unique gas which is obtained by the process of synthesis of two principal gases, namely nitrogen and hydrogen gas. Nitrogen gas is obtained by isolation from air by the method of fractional distillation of liquefied air. Hydrogen gas, on the other hand, is obtained from hydrocarbons by cracking. Now, to be able to synthesize nitrogen and hydrogen, there are three principal conditions. Namely, our temperature needs to be within the range of 400 to 500 degrees Celsius. Pressure needs to be between 200 to 500 atmospheres. And there should be a catalyst because the reaction is slow and the catalyst is finely divided ion. Now, the reaction between nitrogen and hydrogen forms ammonia gas. However, the reaction is reversible. Now, once a state of equilibrium has been attained in this reversible process, we find that as more nitrogen combines with hydrogen to form ammonia gas, so does the ammonia gas decompose back into nitrogen and hydrogen. What then is done in order to ensure that the principal forming substance is ammonia gas? In order to principally form ammonia gas, we fix the optimum condition, which I have stated here as follows, that the temperature is within the range of 400 to 500 atmospheres. However, it is fixed at 450 degrees Celsius as the optimum temperature condition. The pressure should be ascending pressure from 200 atmospheres to 500 atmospheres. And since the reaction is slow, we need a catalyst, which is finely divided ion. Now, the finely divided ion may also be impregnated by aluminium trioxide, which is a booster to the catalytic process. Now, let us look at the critical steps conducted by the flow diagram illustrated above. Now, the Haber process is constituted of 5 principal chambers. The first chamber is the purifier, the second the compressor, the third the heat exchanger, which is intertwined with the catalytic chamber, and then the condenser is the 5th chamber. The main reaction begins in the heat exchanger. However, before that stage, the two gases which are obtained from air by isolation and by cracking of hydrocarbons are purified through a refinery. Now, once they are purified, they are taken to the compressor where they are subjected to ascending pressure from 200 to 500 atmospheres. At that condition, the molecules of gases are closely interacting but not yet synthesized. They are taken to the next chamber, which is a heat exchanger. The thermal characteristics thereon ensure that there is direct synthesis between nitrogen and hydrogen to form ammonia gas. Now, since the reaction is low, we introduce the catalyst, namely finely divided ion, and if the need arises, we impregnate it with aluminium trioxide, which is a booster to that catalyst. Now, the process becomes fast and produces an ammonia gas. In the absence of the booster, we will form roughly 10% of the synthesized gases. With a booster, we will form roughly 90%. And once the ammonia gas has been formed and stability tested, we take it to the condenser. Within the condenser, we fix the temperatures at the melting point so that the gas will sublime gradually will condense gradually into the liquid form, simply because when it gaseous form, it's not easy to contain. And then once it is liquefied, we can collect it by suitable vats and store them in multiple tanks for use in varied industrial processes and other medical and human use. Now, while the gas is being condensed, the unreacted gases are transferred back to the compressor, and when they go to the compressor, the cycle is repeated from the compressor to the heat exchanger, intertwined with the catalytic chamber, and back to the condenser to precipitate the required gas. Now, ammonia is an important gas, and we find that it is used as a smelling salt for overcoming nausea and fainting. We can use it to manufacture phosphate ammonium nitrate salts. We can also use it in the large-scale manufacture of nitric acid, which when combined with nucleic acid becomes the aqua regia, a solution which is suitable for other industrial processes. Now, that simply describes what we are calling the Haber process. What have we said? If I recount it, we have said that ammonia is fabricated industrially on a large scale by the process referred to as the Haber process. The raw materials in the Haber process are nitrogen and hydrogen. Nitrogen obtained from air by isolation, and hydrogen obtained from hydrocarbons by cracking. The synthesis between nitrogen and hydrogen is held back until the two gases are purified, which means refined and cleansed from impurities and other particulates, and then compressed to make the gases or molecules to interact effectively, and then finally heated in the heat exchanger, which is intertwined with the catalytic chamber, which enables the reaction to proceed faster. The catalyst is finely divided ions, which is impregnated with aluminium 3 oxide. The optimum conditions we have said are temperatures are to be 450 degrees Celsius, pressure 200 to 500 atmospheres, and the catalyst finely divided ion. Thank you.